Here we have question 1 of section B. It says a dry cell has an EMF E and internal resistance R and is connected to an external circuit. There is a current I in the circuit when the potential difference across the terminals is V. Now, just to discuss this briefly before we go into it, we will be using this formula over here really, or this is what we're going to develop, that the E is equal to I R plus R. Now, we're not given this, but this would be your R there. So your E is equal to IR plus I small r. And the small r, this is the energy, this is the potential difference per coulomb that is lost within the cell. And this is the potential energy per coulomb that is lost within the circuit. Okay, so that's basically what we're going to be looking at. We're going to actually develop this formula through these questions. So state expressions in terms of E, V, R, and I where appropriate for the total power supplied by the cell. Now, the total power is given by this formula over here. We can use these for power. Now, this E is the total energy per coulomb that the cell can deliver, and it's got a current of I. So the power would be this one over here. Power is equal to V times I. So, and that is the E. So you're going to get EI there. That would be the total power. Now the power dissipated within the cell, we've got this current and we've got this small r here, and that's where you're going to get your dissipation of energy. So looking again at our formula here, we're going to use the I squared r. So that would be I squared, but now we are dealing with the small r. That would be the power dissipated within the cell. And the power dissipated in the external circuit, now this V here is the potential difference after the energy has been lost within the cell. So that is going to be VI. This V is the energy per coulomb that's available to do work and so forth within your circuit. So it'll be VI. So use your answers to A to derive a relationship for V, E, I, and R. Well, this over here is the total power. Alright, so that's your total power is equal to EI, and that equals the power in the cell, I squared R, plus the power in the external circuit, VI. So there you would have your relationship there. We could simplify that down. That's your E, and we could divide all the way through by an I, and we could get V when you divide through by I all the way through. So we get V here plus IR. And I just want to bring you back to this idea that that is this over here. This is your V. I times R is your V from this. V is equal to I times R. And this is your I times your small r there. Okay. So, going over the page, we've got a graph here. Now, just talk about this graph. It's in relationship to the circuit that we've just been dealing with. But here you're looking at V. Now, this is the V across the cell. This is the amount that can be delivered to the circuit. And you see that it's decreasing. As the current increases, your IR squared term increases. So as it increases, your IR squared term, in other words, the energy loss within the cell increases, and therefore the V, because your V would equal your total energy minus this I squared R, the total potential difference minus this I squared R, this V is actually decreasing as your current is actually increasing. So we're going to use that fact later on. We'll come back to that now. Alright, so complete the diagram below complete the diagram below to show the circuit that would be used to obtain the data for which the graph was being plotted. Well, we would need obviously an ammeter in our circuit to measure our current. We're going to need here a variable resistor. Now, why do we need a variable resistor? Because as we vary this resistor here, this variable resistor here, as we vary that, we allow a greater current to flow through the circuits. As we make it very small, this resistance allow a large current to flow. And obviously we would have our voltmeter across there to measure that. So that would be our circuit that we would require. Now here, use the graph explaining your answers to determine the EMF, and then to determine the current in the external circuit when the resistance R, that R of the external circuit is very small, and deduce that the internal resistance of the cell is 1.2 amps. I'm going to do all of this going to take it back, so you keep this side of your question paper available, and I'm going to go back to the graph and then we'll work on it from there. Okay, so the first question that we're wanting to find is use your graph to explain your explain your answers to determine the EMF of the cell. Now your EMF is the maximum energy that can be provided. So let me just redraw this over here. So we've got our diagram here where we have our cell and we have our internal resistance that's got R, and we have our variable resistor, and we have our ammeter, and we have our voltmeter there across like that. Now this V becomes E, heads for becoming E, when your current is very low. When your current goes towards 0, then your I squared R, the energy per unit charge per time, the power lost within the circuit, will head towards 0 also, because your I is heading towards 0. And therefore the amount of energy lost within the cell becomes negligible, and therefore the V will register the E. You can always work out, you can always measure the EMF of a cell by connecting a voltmeter across a cell when there is no current flowing. So if you've got a switch in here, if you open the switch, no current flowing, your I is equal to 0, that V would measure the E. So in looking at my graph here, this value over here, because it's corresponding to a 0 current, would actually be your EMF. So your EMF for that question 1 would equal 1.5 volts. Then it says determine the current in the external circuit when the resistance R in the external circuit is very small. Okay, so here you're making this R, you're heading that towards 0. So basically you're creating almost a short circuit. So you're getting a very large current going through here. So your I is increasing. Alright? And because your I is increasing, we're heading off in this direction over here. Your I is getting bigger. But as you notice here, the V across here is getting smaller. Why? Because the I squared R, the potential difference that is being lost within the cell due to internal resistance, the energy that has been lost within the cell is increasing. So if we extended our graph down like that, this is the point where at this point over here we're at the point where your V is actually it becomes just about 0. Your I becomes very large. All the energy that is being converted is actually being lost within the cell. So the current in the external circuit when the resistance R of the external circuit is very small is this one over here, 1.25 amp. Then it says deduce that the internal resistance of the cell is equal to 1.2 ohms. Now There's different ways that we could do this. Firstly, if I just think of my formula here, that E is equal to I R plus R, like that. Therefore, E is equal to IR plus IR. This IR, the current times the external resistance, is equal to my V. So I get E is equal to V plus IR. You see, we have got a equation which is a straight line sort of graph. Let me just put this in a different color. We got Y is equal to MX plus C, like that. So my I here is my X, corresponds to my X, my E corresponds to my Y. The M would correspond to your internal resistance of the cell. So if you worked out the slope of this graph, because this is your M, the slope of the graph, R would equal this value over here, 1.5 divided by 1.25, that equals 1.2 ohms. So that would give you that value. You can also see from this that your I squared R, because this value over here becomes just about 0, you get your E. Your E becomes IR at that point. Our I is equal to 1.25 times by the R is equal to our E, which is equal to 1.5. So it gives us the same sort of formula for that. Okay, so we have done all of that, and now we just need to go to our last question here. It says the maximum power dissipated in the external circuit occurs when the resistance of the external circuit is the same value as the internal resistance. So we have a R of 1.2 ohms. Calculate the maximum power dissipated in the external circuit. Well, to work out the maximum power, we're going to need our I to work out our I. So we have our EMF, which is equal to 1.5 is equal to I, and we get our external resistance is R plus I, which is 1.2, 1.2. So we get 1.5 is equal to I times 2.4. When I work out what my I is, it works out to be 0.625 amps. Now power is equal to I squared R. From here, power is equal to I squared R. So I get my power is equal to 0.625 squared times the R, which is 1.2, and that gives me about 0.47 watt when I calculate that out.